All right, so using our integrals to find area under a curve, or when we say area under a curve, we refer to that as an area between the curve and the x-axis, right? So what we want to do first is graph our function, make sure our function is continuous on the interval we're looking at, and then locate any x-intercepts. So look for any x values where the function crosses through our x-axis. And then if there are any places where there's discontinuities or x-intercepts where it crosses through, you got to integrate each piece of it, from one x-intercept to the next separately. And then anything that's below the x-axis, the integral comes out as negative, so you take the opposite of it, and then you add all your stuff together. Everybody good with that? Sounds familiar from what you learned hopefully last year. I hope. So if we want to find the area of the region bounded by the x-axis, x equals 2, x equals 5, and the function x squared plus 1, first thing we should do is make a quick sketch of this. So here's x squared plus 1. What do we know about x squared plus 1? It's always above the x-axis. And since it's always above the x-axis and we know it's a polynomial, so it's continuous, we don't have to worry about any discontinuities, and we don't have to worry about any places where it might be below. So all we have to do to find that area from 2 to 5 is just integrate that function from 2 to 5, right? So that'll be the integral from 2 to 5 of x squared plus 1 dx, which is x cubed over 3 plus x, evaluated from 2 to 5, which, what does that come out to be? 125 thirds plus 5 minus 8 thirds plus 2. Let's see, what does that come out to be? 125 thirds minus 8 thirds ought to be 117 thirds plus 3. That's 126 thirds. What is that? I think that divides to be 42. Yeah. And if you want to attach units squared to that, since we're specifically talking about area, that's great. If not, it's not a huge deal. Everybody good there? Or no? Okay. Let's take a look at finding the area between the curve and the x-axis on the interval from 2 to 3 of natural log of x minus 2. So what does natural log of x minus 2 look like? Is it above or below the x-axis from 2 to 3? Yeah, it should be below. We should know it's below because if we had something like the natural log of e squared minus 2, that equals 0, right? And because that becomes 2 ln e minus 2 equals 0, right? Which is definitely true. Okay. So we know that this is below the x-axis because e squared is more than 2 and 3. And if I plugged in, any of those values between 2 and 3, like if I plugged in e, I get a negative value. So we know that this is below the x-axis. And so when we look for the area, our area ought to be the opposite of the integral from 2 to 3 of ln of x minus 2 dx. Everybody good there? And hopefully you remember the integral of ln x is x ln x minus x, and then minus another 2x, evaluated from 2 to 3, which gives us, if we want to simplify that down, x ln x minus 3x from 2 to 3, which will be the opposite of what? 3 ln 3 minus 9 minus 2 ln 2 minus 6. And we could simplify that down some, I think, if we wanted to. What does that become? The opposite of 3 ln 3 minus 2 ln 2. And then what do we have? We had negative 9 minus negative 6, so that's a minus 3. Distribute your negative sign through, and you got 2 ln 2 minus 3 ln 3 plus 3. And if you really wanted to, you could turn at 2 ln 2 into ln 4 and 3 ln 3 into ln 27 and make that natural log of 4/27 plus 3. But any of those answers along the way are fine. Everybody good with that or no? All right, how are we going to find the area between the x-axis and the curve for this one on the interval from 0 to 4? First, what do we need to figure out? We need to figure out when it's got x-intercepts. How do we figure out when this has x-intercepts? Set the numerator of the fraction equal to 0, right? That'd be x minus 3x minus 1 equals 0. So x equals 3 and x equals 1. So we've got multiple x-intercepts here. If I plug in, let's say, something between or something less than 1, like 0, do we get a positive or a negative value? So if you plug in 0, you get a positive. And if you plug in something like 2, what are you going to get? Looks like a negative. And if you plug in something greater than 3, like 1,000, it's going to be positive again. So we know that what we should end up with here for our area is an integral from 0 to 1 of f of x minus the integral from 1 to 3 of f of x dx. And we have to subtract that one because it's below the x-axis. And then plus the integral from 3 to 4 of f of x dx because it's back above the x-axis. Everybody good with that? And just for the good practice for the quiz tomorrow, how do we solve this integral for f of x? What do we need to do first? Since it's a rational function and the degree of the numerator and the denominator are the same, we'll do the division, right? So we'll get x squared minus 4x plus 5 going into x squared minus 4x plus 3. And that goes in once, right? And if we put this below, what do we end up with? Just a minus 2 down there. So let's just figure out, without the limits of integration there, what's the integral of f of x dx equal to? Well, it's the integral of 1 minus 2 over x squared minus 4x plus 5 dx. So how are we going to figure out that integral? First off, the integral of the 1 part's just x, right? And then we're going to have a 2 that we can pull out in front of that. 2 times the integral of dx over, what do we do with x squared minus 4x plus 5? Yeah, complete the square. Good, Darius. So this becomes x minus 2 squared. That's x squared minus 4x plus 4. And then we had a plus 5, so we got a plus 1 attached there. All right. Everybody good with that? And what does this become? This just becomes x minus 2 inverse tangent of x minus 2. And we're not going to have to bother about putting the constant onto that because we've got a bunch of limits of integration here. So let's do this on a new page. We've got, what did we have to start with? We had from 0 to 1, right? So that ought to be right up here. We had x minus 2 inverse tangent of x minus 2, I think. So if we're going to evaluate that from 0 to 1, that ought to be 1 minus 2 inverse tangent negative 1 minus 0 minus 2 inverse tangent of negative 2, which we'll simplify here in a second. If we're going to go from 1 to 3, that's the section that needs to be negative, right? So negative, and then we're going to have 3 minus 2 inverse tangent of 1 minus 1 minus 2 inverse tangent of negative 1. Everybody good with that so far? And for 3 to 4, we should end up with 4 minus 2 inverse tangent of 2 minus 3 minus 2 inverse tangent of 1. And it's a little bit of a mess here. Don't worry, I'm not going to make you guys do all this arithmetic every time. We're just going to use our calculator for some of the ones we go forward with. But let's simplify this one out. So we've got a 1 minus 2 times the inverse tangent of negative 1. So what's the inverse tangent of negative 1? That ought to be what? Negative pi over 4. So we have 1 minus 2 times negative pi over 4, or 1 minus negative pi over 2. So 1 plus pi over 2 minus 0, and then plus 2 inverse tangents of negative 2. So that's the first part. Then we've got minus 3. And then we've got minus a minus 2 inverse tangents of 1. That's pi over 4. So that's plus pi over 2. And then we've got minus minus the 1. So that's plus 1. And then we got minus minus minus. So that's going to be a minus 2 inverse tangent of negative 1. And the inverse tangent of negative 1 is negative pi over 4. So that ends up being a plus another pi over 2. And then we got plus 4. And then minus 2 inverse tangent of 2. And then minus 3. And then this last one becomes a plus, and that's pi over 2. Everybody good with that so far? A little bit of a mess, but that's okay. And how are we going to deal with that? We got a 1. The negative 3 gives us negative 2. Plus the 1 is negative 1, plus the 4 is 3, minus the 3 is 0. So all of those constants cancel out. And we got pi over 2 plus this pi over 2 is pi, plus another pi over 2 plus another pi over 2. So that's going to give us 2 pi plus Okay, sorry about that. It's 2 pi plus 2 times the inverse tangent of -2, and then minus 2 times the inverse tangent of 2. Can we make that any simpler or no? Should be able to, right? I could take the negative out of here, right? We know that the inverse tangent of -2 is just the opposite of the inverse tangent of 2, so I can make that -2 inverse tangent of 2. So this could be 2 pi minus 4 inverse tangent of 2. That'd be fine also. In fact, that's a better answer. But everybody good with that or no? Any questions, any issues? All right. So now we'll move on to finding the area between curves. So should know that in order to find the area between two curves, we just need to figure out which curve is greater than the other one on the given interval, or if they intersect on the interval, because if they do, then you got to break it up into multiple different integrals. And then just take the upper function minus the lower function. And you no longer need to worry about stuff that's below the x-axis if you're doing an area between curves, because if you think about it, if I have something that's above and then something that's below, if I take the integral of this one, that's going to give me the positive value, minus the integral of this one is minus a negative. So that should then add together and give you the right area. So just always take the upper one minus the lower one. And if it's split into two different sections, then split into two different sections and figure it out. Everybody good with that or no? All right, so let's see if we can find the area of the region that's enclosed between x, ln x and 6 minus x squared on the interval from 1 to 2. So how are we going to do this one? First, we should take a look at the graph. So let's do that on Desmos real quick. I think our first one was what, x, ln x? Yeah. And then 6 minus x squared. And so if we're looking at that graph, we can clearly see that between 1 and 2, the parabolic function is always above the logarithmic function. Everybody agree with that? Okay. So this ought to be an integral of 6 minus x squared minus x ln x dx, integrated from 1 to 2. And just to refresh our memories on how to take integrals using calculators, let's do that. So hopefully you got your graphing calculator handy. If not, run and grab it real quick. I'll wait just a second. No, Nick, I'm not planning on doing this one in terms of dy. We're going to do some in terms of dy, but not this one. All right, everybody got the calculator? So should just be math and then option number 9. And with any luck, your calculator comes up like this. If your graphing calculator does not come up with the actual integral sign, then you need to wait a second. I'll explain to you what you need to do with it then. So let's see, what was our interval? Our interval was from 1 to 2, is that right? And it was 6 minus x squared minus x ln x dx. And what do we end up with? 3.030. Is that what you guys got? Good or no? All right. Okay, let's take a look at this one. Let's find the area of the region bounded by y equals 3 on the top. So above by y equals 3 and below by y equals negative x plus 2 and y equals natural log of ex. So let's think about what these look like. First off, let's draw an axis. Try and practice sketching some of the stuff a little bit without Desmos, since you won't have Desmos available to you on the AP test. So there's our axis. Here's our y equals 3 function. And then we got y equals negative x plus 2. Should look about like that. And where do those intersect? Where does y equals 3 intersect with y equals negative x plus 2? Should be at x equals negative 1. Okay. And then natural log of ex. Where does natural log of ex intersect with y equals negative x plus 2? These should intersect at x equals 1, and we should have a general idea of what a natural log function looks like, right? So at x equals 1, something like that. Natural log of ex. So we're looking for the area of the region in between all three of those, right? So this area right here. And what's the problem that we've got? Yeah, exactly, Nick. There's two different functions on the bottom, right? So from negative 1 to 1, the top function is y equals 3, and the bottom function is negative x plus 2. But from 1 to wherever these intersect over here, which we'll have to figure out in a minute, y equals 3 is still the upper function, but the lower function is natural log of ex. So to find this total area, we need an integral from negative 1 to 1 of 3 minus negative x plus 2 dx, plus an integral from 1 to somewhere, which we'll figure out, like I said, of 3 minus natural log of ex dx. And how do we figure out where those two things intersect? Should be able to find that pretty easily just by graphing them both on our graphing calculator. So one of them is natural log of ex, and what was the other one? It's just y equals 3, right? So if we graph those and zoom it so we can actually see, I hit zoom in. There we go. To calculate our intersection point, right? We second calculate intersect, and we pick a point that's to the left of the intersection, and then we pick a point that's to the right of the intersection, and get 7.3890561. Everybody good with that? And so if this was the AP test, you'd say something like 3 equals ln ex at x equals 7.3890561. Everybody good there or no? All right, and then you can just use your calculator to approximate that integral since we've got it set up. The setup's the hard part. I think integrating that's not so bad. So what does that come out to be if you integrate it? Anybody got an answer for that from their calculator? $6.389, good. Sounds about right. 6.389 units squared. Anybody have issues with that or no? All right, let's take a look at this one. Looking for the area enclosed by f of x equals 1 over x squared minus 2x plus 2, and then g of x equals that horrible cubic function. Okay. Not even going to bother to evaluate this one. Let's just get it set up properly. So how are we going to get it set up properly? First off, we're going to see when these things might intersect. When does f equal g? And since we've got Desmos, we might as well use Desmos for now. Otherwise, you can do it on your graphing calculator. What was it? 1 over x squared minus 2x plus 2, I think. And the other one was a mess. I think it was like 3x cubed, and it was minus, I don't know, was it 19 halves x squared? Is that right? Plus 7x plus a half. Okay, and so we can see that those intersect at 0, they intersect at 1, and they intersect at 2. And from 0 to 1, the cubic is above, and from 1 to 2, the cubic is below. And so if we were to set this up, we'd set this up as an integral from 0 to 1 of g of x minus f of x dx plus an integral from 1 to 2 of f of x minus g of x dx. And if we were going to go and do these integrals, how would we integrate the f1? We'd want to do what with it? Turn it into x minus 1 squared plus 1, right? And use an inverse tangent on it. And then the other one is just an easy integral to do. So everybody good with that? We're not going to bother to evaluate that one out. But any issues there or no? On that one, I thought I said, oh, yeah, the area enclosed between them, Shayla. So no interval specifically given, but it's what's enclosed between the two of them. So there's nothing enclosed between them here because they don't cross back through. So it's only just this the two little sections here where it's enclosed. All right. Okay, let's take a look at this one. Let's find the area of the region enclosed by y squared equals x plus 1 and y squared equals 3 minus x. So this one is a good one for us to do in terms of what? In terms of y, right? So we got to make sure we know how to do these in terms of x and in terms of y. So we should have a basic idea of what these look like, but we can take a look on Desmos anyway, just to make sure, right? We got y squared equals x plus 1, which we know is just going to be a parabola, just on its side, right? And that one's opening to the right, because if we solve this for x, it's a positive y squared. And the other one was what? Y squared equals 3 minus x, which if we solve that for x, it's got a negative y squared in it. And so that one should be opening to the left. So, you know, if it's x equals y squared with a positive a value, or a times y squared is positive a value, opens to the right, negative a value opens to the left. Hopefully you're all good with that. And then the reason why we wouldn't want to go and try and do this in terms of x is because we'll note that for some pieces of this, like from -1 to this intersection point at 1, the upper function and the lower function are the same parabola, right? And same with from 1 to 3. But we have one function that is always to the right of the other function for all of the y values going up from, looks like that's -√2 to √2, which we'll figure that out in a second. But the blue function, our y squared equals 3 minus x, is always to the right of y squared equals x plus 1 for all those y values. So we can do this one in terms of y. So first couple of things we need to do is we need to write both of those functions as x equals. So we've got x equals, this one's y squared minus 1, and this one is x equals 3 minus y squared. And remember that the 3 minus y squared one is the one that is to the right of the other one. And so we're going to integrate the rightmost function minus the leftmost function, all in terms of y. And if we're doing it all in terms of y, it means we need to figure out the y values at which these two functions intersect. So we'll set y squared minus 1 equal to 3 minus y squared, giving you 2y squared equals 4, or y equals plus or minus √2. So -√2 to √2. Everybody good so far? And we'll integrate from -√2 to √2. And if we simplify this down, it ought to become a -2y squared. And 3 minus the -1 is a plus 4 dy. So we end up with -2/3 y cubed plus your 4y from -√2 to √2. And what does that come out to be? If we cube √2, that's 2 √2. So that's -4 √2 over 3 plus 4 √2 minus, and then that one's going to become a positive 4 √2 over 3 when we cube the negative and have a negative sign in front of it. And then a minus 4 √2. And getting common denominators and simplifying all that down, what do we end up with? That's a -8 √2 over 3 plus 8 √2. So -8 √2 over 3 plus 24 √2 over 3, or 16 √2 over 3. Good or no? We're going to do another one in terms of y here also, but let's make sure we're okay there. Everyone good? If I put which integral into the calculator, -2y squared plus 4 from -√2 to √2. Are you trying to type it in with a Y? Yeah, type it in with an X. I don't know. You just said oh. You said yeah, oh no. So I'm not sure what to make of that, Nick, but at least you can see the screen now, right? Are you good with that, using the calculator for that integral, or no, Nick? I could do it if you want, but. Well, I'm like trying to figure out what else I'm going to add to it. Yeah. Okay. All right, let's do another one of these. It's going to be in terms of y. So we want to find the area of the regions that are enclosed by x equals sine y and x equals y cubed. So just going to take a look real quick on Desmos, but then we'll do the work on the actual graphing calculator just to get used to it. All right, we should know x equals sine y is just sine curve, but the other direction, right? And that x equals y cubed should be just a cubic, except flipped the other direction. And so if we're looking for the area of the regions that are enclosed by this, well, there's two of them. There's one from this negative 0.801 x value to 0, and one from 0 to that x value of 0.801. Or we could say there's one from the negative 0.929 y value to 0 up to the 0.929. And what do we know about both of these functions? We should know that they're both symmetric. And so that this little section here should be equivalent to this little section down here. And if those two sections are the same, we could just do 2 of one of the integrals. So let's do the one from 0 up to this 0.929 value. And we're going to use the graphing calculator to find the 0.929 value, but we'll write it down here for now in just a second. Everybody good with that to start with? So we're going to do 2 times the integral from 0 to whatever that value we get of sine of y minus y cubed dy. And on our actual graphing calculator, how are we going to figure out where those intersect? We want to know when sine of y equals y cubed, so we can just plug those in as sine of x and x cubed. And if we graph them, now when we're looking for the, since instead of putting in a y value in there, we put in an x value. If we're looking for the intersection point, we want to look at the x coordinate that it gives us, which is 0.9286263. Oh, did I not show the calculator when I was doing that? Must have not shown the calculator anyway. There it is, 0.9286263. Everybody good with that though on the calculator? We'll do it again real quick. So we'll calculate the intersect from a value to the left of that intersection to a value to the right of the intersection, and 0.9286263. And then we can just use our calculator to approximate that integral. And what does that come out to be? I'll let you guys do that. Remember, you're just going to do it all. When you type it in, just type it all in terms of x with a dx. Yes, that's the x value, Adrian. And we chose the x value because, when we plug the equations in, instead of typing y's, and we can't type y's into our graphing calculator, we can only type them in as x's. So we got to use the x value that it gives us. All right. And what does that integral come out to be if you guys evaluate that on your calculator? And don't forget to multiply it by the 2. Anybody? Anybody got an answer there? All right, 0.430. That sounds good to me. Sure, we'll say units squared. Any issues with that? Everybody feel like they could do these in terms of x or in terms of y, and could do them where they're broken up into multiple different integrals, do them either by hand or on your calculator? Any issues with any of this basic area stuff before we move on to more difficult area stuff and new area stuff that you didn't learn last year? Everyone's good? All right, so now what we're going to do is we're going to move into talking about area and polar coordinates. Okay. So before we can even start this, we need to think about a polar curve. So I've drawn a polar curve here. It doesn't matter what the function is, but it's got some point on it, point P, which is an r theta point. And then I've got a little d theta there, which is just a tiny, infinitesimally small angle that we've got going along this curve. Now, just like we have a dx, right, which is a very tiny width of the rectangle, well, this is d theta, is just a very tiny angle that's making a slice of this polar curve. Everybody good with the picture so far? Okay, hopefully so. So what shape is that little shaded region? It's just a little wedge of some curve, isn't it? Well, the little wedge of that curve, I could follow the same trajectory of that curve and turn this whole thing into a, well, that was really horribly done, but into a circle where this chunk is just a sector of a circle. That circle doesn't match up necessarily with the function that I'm looking at. Kind of like when we try to draw rectangles underneath a curve, right? Those rectangles don't match up perfectly with the curve. They just come close to it, right? Well, same with this. The sector of some circle matches up pretty closely with this curve, but not perfectly, right? But it is a sector of some circle going around there. So this shape is a sector of a circle. And not necessarily a sector of this exact little function here, not a sector of a circle that it would fit nicely into here, but it's just a sector of some circle going around. Does that make sense? Hopefully that makes sense. And what's the area of that region? How do we find the area of the sector of a circle? You should know how to find the area of a sector of a circle. How do we do that? Yeah, almost, Nick. So it's pi r squared, right? That's the area of the entire circle, times our theta. Well, what's our theta in this case? It's a d theta. That looked horrible, so we're going to rewrite it. D theta divided by the entire circle, right? Right, because we have d theta radians out of 2 pi radians of this circle, of the full circle. So instead of it being pi r squared d theta, we got to divide that by 2 pi. Everybody good with that? Or no? Okay, so then if I want to use that to find the area between the origin and some polar curve, I should be able to just sum together an infinite number of these infinitesimally small sectors of circles going around it from some alpha to some beta that I choose. So if I wanted to go from 0 to pi over 4, let's say I could go from 0 to pi over 4, and I would just use this formula. Right? We know what r is normally for any polar curve, and then we'll integrate it in terms of theta. So how can we simplify this though first? We can get rid of the pi's, right? So if we were to integrate 1/2 r squared d theta from alpha to beta, that ought to give us the area from alpha to beta on any polar curve. Just like we sum together an infinite number of little rectangles for rectangular coordinates, for polar coordinates, we sum together a bunch of little sectors of circles that are infinitesimally small, have this infinitesimally tiny angle to them. Does that make sense to everybody or no? So I think I have it written. No, the theta value of that point doesn't matter at all. Remember, it's just like when we did the rectangles, right? It doesn't matter which arbitrary rectangle we choose, as long as we make them, there be an infinite number of those little rectangles and we sum them all together, that gives us the full area. Well, same thing here. It doesn't matter specifically where I draw this one sector, because the point is that they're infinitesimally small and I'm making an infinite number of them from, alpha to beta to figure out the area from alpha to beta. Does that make sense, Nick? Cool. Everybody else good or no? So here's the formula. Sometimes it's written as 1/2 of f of theta squared d theta, but this is our area between the origin and any polar curve. So let's do one of these. Let's see if we can find the area of the region in the plane that is enclosed by the cardioid r equals 2 plus 2 cosine theta. So it's been a couple of months now since we started and talked about polar stuff right at the very beginning. What does the cardioid 2 plus 2 cosine theta look like? Which sections or which quadrants should have the majority of this curve in it? Since it's a positive cosine, it should be mostly in the quadrants where cosine is positive, right? It's going to look sort of like that. That's pretty terrible, but in fact, I'm going to redraw that because that was really terrible. That's still really bad. We're going to call that good. That's better. So this right here is out 4 units. Okay. And most of it's in quadrants 1 and 4, with a little bit in quadrants 2 and 3. But we know that it does take 2 pi radians for this to go all the way around. And so if we want to find the area of this region, it ought to be 1/2, because it's 1/2 r squared. So 1/2 of the integral from 0 to 2 pi of r 2 plus 2 cosine theta squared d theta. Everybody good with that setup? So it's squared because that's exactly what we got in our formula before, right? We said pi r squared d theta over 2 pi. The pi's canceled, so it's always r squared over 2, or 1/2 r squared d theta, just because of the formula for the area of the sector of a circle. Good, Nick, or no? Okay, so then what we got to do is we got to distribute all that out. So we got 1/2 of the integral from 0 to 2 pi of 4 plus 8 cosine theta plus 4 cosine squared theta d theta. And what do we get there? We get 1/2 of 4 theta plus 8 sine theta for the first two. And then we could take the 4 out of there, and the 1/2 makes it into a 2. So 2 times the integral of cosine squared theta d theta. Everybody good with that so far? So this becomes 2 theta plus 4 sine theta plus, and then cosine squared theta is going to become a 1/2 of 1 plus cosine 2 theta. So we'll turn that into just an integral of 1 plus cosine 2 theta, since there's already a 2 out in front of it. Hold on one second. Okay, sorry about that. And so we've got, still keep my 0 to 2 pi on here. And if we integrate the 1 plus cosine 2 theta with all the rest of this, what do we have? We have 2 theta plus 4 sine theta plus a theta, and then what was it? Plus 1/2 sine 2 theta, I think. And we're going to evaluate all of that from 0 to 2 pi, which ought to give us 4 pi. And then the sine of 2 pi is 0, so that's 4 pi plus 0 plus theta, so that's plus 2 pi. And then plus our 1/2 sine 2 theta, so that's 1/2 of the sine of 4 theta, which is still 0. And then minus 0 plus 0 plus 0 plus 0. So it looks like we end up with 6 pi units squared. Any issues, problems, questions with that, or everybody good with that? I assume that means everybody's good. All right, so let's see now if we can find the area of the inner loop of the limestone r equals 2 cosine theta plus 1. So any thoughts on how we're going to figure out the inner loop of the limestone? First off, let's just sketch what this looks like. So if we start at theta equals 0, that's going to start us all the way over here at 3. And it's going to go this direction until, oh, that's really bad. It's going to go this direction until it comes around and hits the origin, has this little inner loop, comes back around and looks something like that. So it's going and traveling in this direction. And our inner loop always has the cusp of that inner loop at the origin. So we need to figure out when is the R value equal to 0 on this limestone. And there should be 2 places, and we'll take the first one. and integrate to the second one, and that ought to give us everything in between or inside of this inner loop. Everybody good with that or no? Hopefully. So 2 cosine theta plus 1 equals 0, and cosine theta equals negative 1/2. So when does that occur? At theta equals 2 pi over 3 and 4 pi over 3. And so those will be our limits of integration. And we're going to go in and say this is an integral from 2 pi over 3 to 4 pi over 3, and have a 1/2 out in the front, and our r value squared, 2 cosine theta plus 1 squared d theta, and distribute out the 2 cosine theta plus 1. To 4 cosine squared plus 4 cosine plus 1. And the first part of that should be easy enough. All right, first part of that ought to become 1/2, and let's see, now I've forgot what it was. Not the first part, the second part of that should be 4 sine theta plus theta. Which is going to have to be evaluated from 2 pi over 3 to 4 pi over 3. And then we're going to have, once again, we're going to have the 1/2, and we can pull the 4 out, which makes it a 2, and then the cosine squared is going to get a 1/2 when we do the power reducing. So all of those constants are just going to cancel out, and we'll just have a 1 plus cosine 2 theta. And then we'll distribute the half through and integrate and put it all together. So we're going to have a 2 sine theta plus a theta over 2. This one's going to be plus a theta, and then that one's going to be plus a 1/2 sine 2 theta. And all of that from 2 pi over 3 to 4 pi over 3. So 2 sine of 4 pi over 3, what's the sine of 4 pi over 3? Ought to be negative root 3 over 2. So 2 of those ought to be negative root 3. And then plus half of 4 pi over 3 is 2 pi over 3, plus the 4 pi over 3. And then 1/2 the sine of 8 pi over 3. And sine of 8 pi over 3 is the same as the sine of 2 pi over 3. So that should be root 3 over 2 divided by 2. So plus root 3 over 4. And subtract, and then 2 times the sine of 2 pi over 3. That ought to just be root 3. So it's root 3 over 2 times the 2. And then half of that is pi over 3 plus another 2 pi over 3. And then plus 1/2 sine of 4 pi over 3. Well, that ought to be a minus root 3 over 4 when we divide the root 3 over 2 by 2. Everybody good there? Hopefully that's good. And 2 pi over 3 plus 4 pi over 3 is 6 pi over 3, or 2 pi minus a pi in there just gives us pi. So we got pi minus, and then what do we got? We got a negative root 3, and then this is going to be minus this root 3, so that's negative 2 root 3. And then we've got plus and plus the root 3 over 4, so that's plus 2 root 3 over 4 plus root 3 over 2, so that ought to be minus 3 root 3 over 2. Everybody good there or no? Any questions or issues with that? That's where we're going to stop for today. Everybody good or no? Nobody's really responding, so I know this is new stuff, but the integral shouldn't be the part that's tripping you up. So units squared if you want to put them, yeah. Everybody okay with that process and how to find the area on a polar curve? All right. So tomorrow we're going to finish up talking about area with polar curves by throwing more than one polar curve up there and finding like the sections between them. So we're going to do a little bit more with that. That'll take us probably about half the time, and then we'll end up talking about volume after that. So that's our goal for tomorrow, is to do the rest of polar area and to get through the majority of the volume stuff. We may not be able to get through all of the volume because we got to take the quiz tomorrow on partial fraction, decomposition, integrals. Any questions on anything? Are we all good?